Hello and welcome back to RAS Technical Sessions. It is January 20th and we have a really great presentation. Before we start, just going to give you some news on a new board member that's joined us. Christopher Goodrick of Applied Industrial Technologies is joining us to help with the planning and whatnot. New sponsors for 2022, Applied Industrial Technologies and Castle Surface Technologies, that's corrosion and abrasion solutions. And March 17th, we're really hoping to be back in person at Full of Social Lounge. It didn't make sense in January because, you know, provincial restrictions didn't allow us to mingle. So that was the whole point. Golf tournament, June 23rd. Again, really hoping this is going to go through. We've missed 2 years already. We're going to try and really make that happen. And lastly, I want to mention the MRO Technical Conference and Workshops, October 26th and 27th. So we've got an open call for presentations. Go on the website, download it, and we'd really love to see you presenting. And a shout out to our friends at Calgary Pump Symposium, May, I want to say 12th and 13th this year, if I got those dates right. Looking for a social media director because I'm too old for that stuff. But really, yeah, we're looking for somebody else to help out with that sort of stuff. So if you have someone in mind, let us know. I'm going to pass it over to Jared. We're going to do our introductions and get on with it. Thank you very much.
Perfect. Okay. So yeah, we've got Ramneek Sharma, who is a vibration analyst category 3 and customer support at Prognost. Quick bio is Ramneek has been providing customer support and diagnostic services for Prognost since 2016. He performs vibration analysis of rotating as well as reciprocating machines, focusing on improving the reliability of equipment and eliminating bad actors by implementing correct strategies for maintenance. So the title of the presentation is Condition and Performance Monitoring of Reciprocating Compressors. And the quick abstract overview is reciprocating compressors are often some of the most critical process equipment at any given facility. Disruption to their operation means lost production and lost profit. Condition and performance monitoring of these assets can be a very good return on investment. Prognost systems and services are based upon 25 years of technical experience and competence in the acquisition, automated evaluation, and interpretation of condition data of rotating equipment. Since 1990, they have ensured that condition monitoring and machine protection technologies are a safe, reliable, and economical operation for end user process machines. So with that, I will turn it over to Ramneek to take it away.
Thanks, Jared and Andrew, for an opportunity to present the techniques we are using to do the diagnosis of these machines. Before starting, I just want to thank everybody who is joining this webinar and giving their time to brief our technology across the globe who are attending the program. Just bear with me because the number of slides we here are too lengthy session, but maybe I try to skip some quickly because I think there are just the basic things that I need to cover. Okay, without wasting time, I'm gonna start with a basic company profile. We have that we are based in Germany and producing all of our system in Germany. Everything we do R&D for developing our software, hardware, and all other research and development would be held in Germany. We have more than 25 years of experience in this field, and we are very much closely associated with our users and taking their suggestions to implement that in on our system. Yeah, as I mentioned, we have some subsidiaries. One is in Houston, another one is in Abu Dhabi, and total employee strength of 85. Okay. And we have a global sales and service network with a partnership of different vendors and different associates. These are the list of companies that are using our system globally for rotating as well as a recipe machinery monitoring. Okay, this is a list since 2018, not yet been updated, but there are some more in our list. Okay. Okay, let me adjust. I'm trying to take this bar away, which is go to webinar, and then I'll start. Just bear with me. Sorry. Okay, starting with the general concept of compressor monitoring. Again, the objective is to be safe operation and make the machine reliable and efficient. Okay, so this is a basic objective of any online monitoring system that we are using in our plant and machinery. But there are some strategies and some steps that need to be taken to achieve these objectives. So the basic concept of condition monitoring is to acquire the right data from right place or right position on the machine with the right sensor. That's important. So you acquire the data and then you compare that vibration reading, or either it's you are using a vibration monitoring system, temperature monitoring, or whatever, but you need to compare that readings with a threshold. Okay. Once you have a threshold rightly set, the system will issue an alarm and give you an indication that something is going abnormal in the machine, or there is a deviation in the vibration of, or a good vibration is converted into the bad vibration. Okay, and subsequently you do the root cause analysis if system fails and things like this. But the main aim is to put a right sensor at right position and putting the right thresholds. If you achieve these three steps, you make your machine reliable, and you can work quite reliably on the condition-based maintenance. Okay. In the past, we usually don't give much importance to the recip monitoring thing. Maybe I think I've seen a lot of plants in Canada or globally where people just say, okay, just putting a one sensor on the frame vibration help me in protecting the machine. But this is not true to the extent. The thing is that you put a sensor or a velocity sensor on the frame and getting a trip, right? A vibration switch and getting a trip. The thing is that the vibration velocity is the last one to get an influence when you have something going wrong in the crosshead or in the valves. Okay, we are learning this part in a later slides, but the thing is that you may not able to avoid the secondary failure or secondary damages in the machine with the velocity sensor. You may get a trip, but may not achieve the function of the system. If you are putting a condition monitoring system on your machine and putting just a vibration switch, you may not able to avoid the secondary damages in the system. Okay, and you may not able to locate the fault, where exactly the fault lies in the recip machinery. Okay, and people are just focusing on, okay, rotating machines are much more important than the recip, but at least in the upstream or in the plants where you have services like hydrogen and ethylene, these machines become critical on the aspect of the safety point of view. So in that case also, you need to put a right system and right number of sensor on your machines. Okay, but people are getting aware, more awareness is there, and they are trying to put the sensors at the right location and taking the benefit of the technology that are existing in the industry, right? And sometime you don't have a redundancy in the system, then also you are putting a condition monitoring or a safety system on your machines. So here we are talking about the three concept theory of the system, of the MMS system that you may use in your plant, and that is a protection system. And on the protection system is further provides the data to the condition monitoring software. And now in the technology that are coming up, you do the auto diagnostics on that particular data, like machine learning, AI algorithms, digital twin, all you can do on the data if you have. But if you don't have a correct data, you can't able to achieve neither the condition monitoring nor the auto diagnostic functionality. You may trip the machine, you may protect, but at least you are not able to achieve the function that you are able to do the root cause analysis, that what's going on in the system. Okay. So coming to these, this concept of condition monitoring, one is a protection rack. You use this rack as a data acquisition system. The sensor will be placed on the machine, and these sensor would give the signal to the input card integrated in this rack. And this rack will perform a tripping functionality or safety system. Okay. And then this safety system further on giving a stream of data to the condition monitoring software. And this software will process the data, and you put different algorithm statistics to and give the tools to analyze the data in effective way. Okay. After that, in this software, now we have a machine algorithms which do the machine learning part. So you just put the system on your machine, make the machine to learn, and subsequently the all the work would be done by the system itself. And in Prognost system, we call it as pattern recognition, that whenever you have a situation that you have a failure in the past, the system will recognize this failure and it will intimate you before the time with a probability. Okay. This is the rack, and rack should be still certified. In some industries, we call it as we want to buy a SIL 1, SIL 2, SIL 3, which certification of the SIL you want to put in as per your standards or as per an IEC standards, right? And then the system will issue you a shutdown, alert, or unsafe. Basically, when we talk about SIL, what exactly the SIL means in the brief term? Maybe some of you, some of the guys here in the presentation knew what exactly the SIL, but I just want to give you a brief introduction. So SIL is a safety integrated level. It means like if I have a sensor on the machine and this sensor is connected to a wire, and then this wire goes to the junction box, and from the junction box it goes to the connectors and then connected to the data acquisition rack. Okay, and from the data acquisition rack there is a data acquisition card, and then from data acquisition card it goes to the protection card. Okay, this is the flow of the signal from the sensor to the protection card, which trips the machine ultimately. So the basic aim of the SIL is that system should be capable enough to detect any loop issue, any connection issue in the complete signal line, so that the system should not trip it in the false alarm condition. Instead, the system will issue you an unsafe. So here, if you look, there are three parameters. One is unsafe, alert, and shutdown. You know what exactly the shutdown system trips the machine. Alert is just before the shutdown. An unsafe condition is the condition when there is a fault in the loop or in the connection. The system will diagnose this as an unsafe instead of tripping the machine. So this is the basic motive of the SIL, that the system should automatically detect any issue with the loop or either the connection or either the sensor, right? This is a basic description of the SIL. You can go in the document. There is a lot of ISO documents where there is a complete description, but this is very brief or an overview of SIL. So it's really important when you are going in the market and try to find out which system is required as per your requirement. You need to find out whether you need a SIL 2, SIL 3, or even SIL 4 system from the system. But important to check at the level from the sensor to the data acquisition, not from the software side. Software is important, but more important is you just calculate the SIL level according to the loop from the sensor to the protection card. Okay. Then it comes to the condition monitoring software. The stream from the data acquisition rack goes to the software where you have all the processing. You will do the online signal, you do the trending, you do the waterfall plots, early failure detection, wear and performance monitoring, putting an alarm and getting an alarm history. Then you have a transient plot. Some people call it as transient. We call it as ring buffer. So you get all these plots in the software. But basically, if you get the right signal with the right sampling rate from the sensor, then only you will able to do all this stuff. So first and foremost thing is to putting a right sensor at right position, and with the right sampling rate, you capture or digitize the data, and that digitized data would be further processed to get all these plots. And further to that, you will put your thresholds, that is a software alarms, and subsequently you will get an root cause analysis or early failure detection of the system. Okay. Then one step ahead to this thing is a artificial intelligence and machine learning. You make the machine or system to learn about the failures you had, or we also have a library of failures in our system. And when you have that pattern which resemble to the failure library in the system will issue you the text message, give you a notification with the probability of that particular fault. Like in this case, if you see the example here, it says there's a discharge valve issue on the crank end with a correlation of 55.2%. Definitely, these are the helping tools, but ultimately you need to look into the complete system. It will guide you, if it will give you the direction, because here, like in this case, you have 55% of probability. So means, yes, there is a chances that this fault exists, and then you need to dig in more details. Okay, how the vibration behavior, how the signal look like, is there in a valve opening and closing at correct time or not? Then only you will able to get your get this statement verified. Okay. Meanwhile, we also have some poll questions, right? So I am going to the poll. If Andrew can ask one of the poll questions from this to answer.
Okay, so yeah, we're gonna do what the launch here. Are you more interested in early failure detection or protection? So we got 4 choices. Early failure detection for condition-based maintenance, earlier failure detection for time-based maintenance, only protection to avoid big issues, or both A and C are important for me. So the polls are open. We're going to try and get through these fairly quickly, so see if we can tally them up quickly, and then that way we don't take too much time from Ramneek, because he's got a lot more slides to go, and I certainly don't want to cut him short. So I'm going to give it a little bit more time. The votes are coming in, kind of slowed down a little bit, so I'm going to give it 5 more seconds. Okay, we're going to shut it down here. I'm going to see what our results are. Share. Okay, so 36% are looking for early failure detection for condition-based maintenance, only 4% for time-based, and 4% for only protection, and 57% said A and C. So it seems like condition-based maintenance is getting quite popular.
Yeah, I think it is both, like as you said, 57%. So you put a protection on some of the sensor, and then further on processing the signals to get early failure detection on the condition-based maintenance. And I think that's the right way to approach for any CMMS system. Definitely you look into the other parts as well, that how critical the machine is, and whether it's a single line, you have a redundant machine, or what service it has been equipped with. Okay, no problem. So coming back to the concept of the compressor monitoring, there are different sensors that we use to do the do the protection as well as the early failure detection. We will see which sensor we basically use for the protection and which for the condition monitoring. Like in this case, for the dynamic signals coming from the speed, frame vibration, rod position, crosshead, and motor vibration is basically used for the protection of the machine. Okay, and the sensor which is used in the DCS, which is going directly to the DCS, are sometimes knockout level of knockout drum, lube oil pressure, which is an API requirement, then pressure and temperature, interstage pressure and temperature. In some cases, people use different philosophy in the DCS to trip the machine. But from the perspective of condition monitoring system or a vibration monitoring system, rod position, crosshead vibration, frame vibration are basically used for the protection of the machine. Okay, and cylinder vibration, dynamic pressure for the performance monitoring are being used, and these are the sensors that are used for the condition monitoring as well. So the red one here you see are more like a protection signals, and the yellow ones are more like used for the performance and the condition monitoring. Okay, subsequently you club them together and do the analysis, and you can plot trend, online alarms, ridering monitoring, a lot of other stuff you can do from these signals. But basically the rod position, crosshead, and frame are three important ones that is used to trip, and cylinder vibration and dynamic pressure is for the performance and the condition monitoring thing. It doesn't mean that a rod position and crosshead doesn't participate in the condition monitoring, just only to distinguish between these different sensors is to know, okay, which are my protection loops and which are my condition monitoring loop. Okay, frame vibration was an API requirement and is an API requirement currently, but from the fifth version of APS 670, crosshead and rod position are also the part of an protection logic as an optional sensor. But in coming slide, I'll explain you why these sensors are important. Apart from the frame vibration, which is the general concept in the industry right now, that the frame vibration, if I can use, I can do a lot of things, but I'll show you these things in the later coming slides. Okay. So here is a basic challenge in the industry, like how we can reduce the maintenance budget and increase the efficiency of the machine. This is a challenge in front of every reliability engineer, right? So what is the solution to increase the mean time between maintenance? And to increase the mean time between the maintenance, you need to find the weakest links in the chain. So in recipe word, walls are the weakest link in the chain. So if you able to monitor and detect an issue in the walls, you may able to achieve this or may increase the mean time between the maintenance, right? But again, coming to that point, only the frame vibration will not help you achieving this goal, because valves are more like an impacts, and these are high frequencies. And if you are putting a velocity sensor on the frame, you will get a trip when, in the case of when you have a too much an issue on the machine, you will get this response on the velocity at very later stage. By that time, your valves are totally damaged. Okay, so again, coming to this slide back again, if you are able to achieve or able to diagnose the issue on the valves, you'll able to increase your PF interval, the lead time. Okay, and I will have some examples as well that how you can able to achieve that. But ultimately, if you have a correct positioning of the sensor and correct sensors in place, you will be definitely able to achieve this thing. Okay. So I'll going to the machine overview, like the basic schematic and the different machine type. Like in this case, you have two type of machine. One is a hyper compressor that pumps approximately 500 bar of gas, and another one is an API 618 compressors. Most of the industry in this region, or at least in Canada, we have all API 618 compressors. I think only one or two plants in Canada that are having a hyper compressor for ethylene service producing a polymer, but only not much. But in most of the cases, it's an API 618 compressor. So we are focusing here mostly on API 618 compressor, which is a horizontal type of design. And this is basic components, and we need to place a sensor in the way that it all these components would be monitored by the system. This is the actually aim. If you have a piston bands or rider bands, packing, cylinder, valves, crosshead, connecting rod, bearings, connecting rod bearing or a crosshead bearing or a crankshaft bearing, we need to monitor all these components, right? Before it went into a secondary failure mode situation or a catastrophic failure, right? We don't want to wait for the system to activate a trip on the velocity installed on the frame, right? So this is the basic objective. Now, to achieve this objective, we need to place a specific sensor as specific location. So first and foremost sensor is the crosshead vibration sensor, which is an acceleration sensor. It has to be mounted on the crosshead. As we are not able to retrofit these sensor inside the machine, we try to put on the top of the casing on the ribs where the crosshead is connected or shoes are connected. Okay. Then comes a cylinder vibration. A cylinder vibration sensor, again, the placement is important, has to be placed in the position where it captures the signal or a response from each and every valve opening and closing event. Okay, again, this is an acceleration sensor. Now, a proximity probe, which monitors the dynamics of the rod as well as the position of the rod. So dynamics is more like a vibration, how the shaft rod is moving. Position is how shaft is or rod is going up and down in relation to the reference position. Okay, and not but the least one, the pressure transmitters that are integrated directly into the compression chamber. These are the pressure sensors, 4 to 20 milliamp sensors, and these sensors help you to plot your PVs and PT curves. And definitely then you can draw the performance curves as well, like efficiency, volumetric efficiency, suction efficiency, flow balance, all these stuff can be achieved by these sensors. Okay, this is basically for the monitoring of the valves, monitoring of the compression chamber itself, as well as the performance of the machine, how efficient your machine is. Okay, then you have a trigger sensor, very important part, because you need to synchronize the signal. So it is kind of a time synchronization of all the signal in relation to your trigger signal. So the trigger signal knows what is your crank rotation is. Okay, and when the system know what exactly my crank rotation is, with the help of a cylinder vibration, you'll able to tell what is the position of my valve opening and closing event. So you need to synchronize all the signal in relation to your trigger signal to perform any type of diagnosis. Okay, so if you look on these signals, and last is frame vibration, that is velocity. If you look this picture, there are some icons that are bordered with a magenta line. So this magenta line indicate these are your protection loops or loops on which the system trips the machine. and the other ones are only for the condition monitoring. Okay. Now, if you look into this this picture, you will see all the sensor except the frame vibration are the acceleration, and one is a proximity. So acceleration is more important parameter than the velocity for a reciprocating machine diagnosis. Okay, so try to understand that why acceleration is important than the velocity. I'll explain you in coming slide. So this is a schematic for the vertical machine. Same thing, same sensors. So nothing unusual, just in some cases in vertical machine you have a proximity probe, and in some cases not. Like in case of Levy, people sometimes try to put a proximity probe and sometimes not. So it's a choice depending on, right? But this is the same thing in the horizontal, and same way you have a vertical schematic of the sensor location. Okay. Now, so as I said, there are three types of sensor. One is a proximity, another one velocity, and an acceleration. So what is the difference? Here's the difference. Look at the signal type. From acceleration, you get a high frequency signal. From velocity, you are getting a low frequency, and the proximity, it is very, very low frequency. So when I say low frequency, what is a low frequency means in this case? When I say a sensor signal that cutoffs at somewhere around 2 to 2.5 kilohertz, it comes into the range of velocity. And when I say that you have an issue with a crosshead, or if you have an issue with the valves, I am talking about the frequency that is high frequency content, somewhere around 5 kilohertz, 7 kilohertz, 8 kilohertz. So these events would not be able to capture with the velocity. It is just a response after you getting that machine is shaking, and then only you able to trigger the shutdown from this machine. So this is really, really important to understand that what you are going to achieve with different type of sensor. Putting an accelerometer on the valves give you a indication of the valve events, not the velocity sensor. Same way, if you have an issue with the lubrication on the pin in the crosshead, then you need an acceleration sensor, not the velocity. So choose proper sensor, place it at right position, you'll be getting the result, I'm sure. Okay, but your system should be able to capture all the signal. Not only sensor, but the system should also have the capacity to process the high frequency signals. So if you take a system having a signal capacity to process only 3 kilohertz or 4 kilohertz, you're not able to achieve this thing. So the sampling rate of the system should be high enough so that it can cater the high frequency signals. For proximity, we are more focusing on the positioning, like whether the rod is moving up or down, as well as its motion. Okay, so motion gives you the dynamic in the signal, and the reference position give you the whether the shaft or piston rod is moving up because of the lubrication, or maybe going down because of the rider ring wear, if your sensor is positioned at the top of the piston rod. Okay, so this need to be understand like what choice you are going to make for your system, okay, and what you want to achieve. So just a comparison between the different type of machines and how we usually monitor. I think everybody knows like a centrifugal machine are a constant load machine. So you will see everything in the frequency domain. We know we have a bearing, it has inner race fault, it has outer race fault. We know the frequencies where it is coming. But in case of recip word, it's not the case. You don't have we don't have a frequency where the frequencies are existing. We don't have predefined frequencies like a ball pass or cage frequency. In this case, we need to live with the time domain. signal. So we need to work only in the time domain, not in the frequency domain. So if you are purchasing a system that process do the FFT and a lot of things, but ultimately you'll able to achieve the result more precisely in the time domain in case of reciprocating. Yeah, in case of centrifugal machines, you'll able to do a lot of stuff with an FFT, fast Fourier transform, half spectrum, full spectrum, a lot of things you can do. But in case of recip, no. We need to work on the time domain. Okay, we're coming to that part as well, how we are doing that. So these are the comparison of these two signals from two different machine type. One is a centrifugal machine, another one a recip machine. In centrifugal machine, you see the signal is quite sinusoidal and it's quite stable. So means the load is very stable in one cycle. So this is a one cycle. We plotted the signal of one rotation. So you see that the load is continuously the same in the complete cycle. While in case of recip word, the load is continuously changing in each rotation. So in one rotation, you have a tension, and in the same rotation, you have a compression loading on the machine. Okay, that's why it is good to plot and see time domain than the frequency domain. And when you plot your pressure curves in this time domain signal in relationship to the trigger sensor, you'll able to know the correct positioning of your valve opening and closing events. So it's like your car. So if your car engine is getting a right timing, you'll have a spark at correct place, you'll be getting a efficiency. So if by some reason you have a change in the timing of this spark happening in your machine, you'll having some kind of an efficiency loss, or you have some abnormality going on. Same way, if you are plotting these curves in time domain and plotting against the pressure signals, you will able to see where is my valve opening and closing happening, and what is my good and what is my bad situation in the machine. It's very simple. It's an intensity of the vibration in relationship to the timing. So if I know the timing by knowing my pressure signals, I'll be able to see the comparison of good behavior and the bad behavior on the machine. Okay, there's an example coming up for it's an issue of the crosshead pin. This is a good situation of the signal. Signal looks normal, no increase in the vibration, continuously the same. And when they have a high vibration, it appears to be too much of vibration increase at different crank angle. But if you plot this signal and this signal in FFT, you may see there is a slight increase in the vibration in high frequency region, but you'll not able to get an alarm at right time. While if you compare only the time signal in relationship to the bad condition, you will definitely able to see the deviation in the signal. The reason being, when you plot an FFT, you average out the signal and you do the overall vibration measurement if you are plotting a trend, right? When you plot an overall vibration, in this situation, you may get a bit increase, but there are some situation when you don't even see there is there is a major increase in the trend behavior. So if you compare the time signal with a good situation and bad situation, you'll be able to find out much more than just plotting an overall vibration or an FFT. So in this case, this is a crosshead pin issue. There is a high vibration in machine got tripped, and during inspection, they find out that they have the plate holding down. This one has been cracked, right? There is a complete story behind, but because of the time, I'm trying to make it fast. So this is the situation, okay? Right? So again, focus on the time signal, then the frequency domain. There's a technology developed by the Prognost which is called segmentation of the signal. So in this one, I try to explain this is actually a proximity probe signal, but we are making some analogy like a machine speed and the patch of 120 kilometer. Okay, so imagine this is your trip level of 120. Okay, this is your trip level at 120, and I have this signal. So if I try to plot or average this signal, what I will be getting? If I average this signal and try to get an overall, I will be getting 80 kilometer per hour, which is not exceeding the limit, correct? If I divide this signal in two parts, I'll be achieving different values. In one case, 85, another case, 75. Now imagine if I split this signal, not averaging up, and splitting the signal in different portion, I will see that at one point, this vibration exceeds the threshold or exceeds the trip limit, right? And with that, with the experience we have 25, we saw that this philosophy work perfectly, and you can get you can avoid a catastrophic failure in the machine, because it is more toward more conservative practice for protecting your machine before something goes wrong. But if you are plotting just an overall vibration and try to trip the machine, you may lose the events. You may not able to trip the machine like I showed you. If you average the signal, you may not be at that level. And when you have an issue on the crosshead, it is not that much of high intensity, because we are talking about the high frequency. High frequency has a low amplitude, right? And we need to capture that low amplitude signal. So first thing, to capture the low amplitude signal, and after that putting a right threshold on right place. This can only be achieved by these segmentation analysis. So you divide the complete revolution in 36 segment, and then yeah, this is when one case you divide, and another case it is just an overall vibration. In velocity, we never segment because we know there is not too much of frequencies inside the signal, so we only do the overall. But in case of acceleration, like a cylinder vibration and the crosshead vibration, we'll do the segmentation, and we divide this signal in 36 individual parts, and each individual part has its own intensity, and on that we put the thresholds on. So first warning, second warning, and third warning, these are the software based, and the last not but the least, which is a protection limit on the machine. So this is how the system work. Every system in the market works differently, but this is how we are doing the things. So it's your choice how you think, okay, whether you need to go with the segmented analysis or an overall. But from my experience, I must say that overall vibration protects your machine more precisely than the overall monitoring system, and putting the limits on that one. Okay. Now, I think we don't have much time. I quickly go to the crosshead vibration. So as I said, the crosshead vibration sensor is used to detect the mechanical damages on the crosshead, on the bearings, or on the piston rod. Clearance in the drivetrain. So if you have a loose piston nut or loose crosshead itself, cracked crosshead, anything related to the drivetrain in the recip machine would be detected by the acceleration sensor mounted on the crosshead. Okay, loose connection in the pin or piston or lubrication thing, everything would only be detected by the crosshead sensor. So now think of if you are putting on the velocity sensor on the frame. Okay, so this is how we divide the signal in 36 parts, and this is how the signal look like. And these are usually two impacts in ideal situation. What are these two impacts? These are the rod reversals. Okay, everybody know what exactly the rod reversals are? The point where the machine or a piston experience a change in the rod from tension to compression. So if you look at these points, these dots, these are the rod reversal points. And whenever you have a high vibration on these points in the crosshead vibration sensor, it means there is an issue with the drivetrain integrity. Okay, and subsequently you can have another statistics as well, like calculating the compression load, tension load, rod reversal start point, end point, and things like this. You can derive a lot of things, but the basic objective, if you have a high vibration at these points, there is a seriously something is wrong. Here is an example to that. Here's an example of loose piston nut. You see, this is a high vibration at the rod reversal points, and it is increasing over the time. Had an inspection here, and they found that, okay, and I think I missed one slide. Yeah, this one, sorry, I skipped the poll. So they found that there is a loose piston nut on this drivetrain. So going back, you need to monitor these rod reversals. And again, these rod reversal can only be achieved with an acceleration sensor, not the velocity, because see this signal. This signal is almost approximately of 5 to 10 kilohertz. So putting a velocity 2.5 cutoff, gone. Your signal is nowhere. You will not see anything, right? So sorry, Andrew, I'm going to skip the polls because we are not having much time. So going to the cylinder vibration, again, it's an acceleration sensor placed on the head of the cylinder, and it is used to detect the valve impacts, broken plates, valve cage issue, leakages, sticking valve, and things like that. Everything in relation to the valves would be detected by the acceleration sensor placed on the cylinder, right? Same way, acceleration, but now you see this signal looks totally different than what you see on the crosshead, right? Crosshead vibration intensity are lesser, while the cylinder vibration intensity is much higher because of the valve events. But these are inherent, means it's there, it's always there. So we divide this signal in 36 parts, and you see, you know the intensity. And again, when you plot this vibration signal, cylinder vibration, in relation to the pressure, like you see this blue one head end pressure and red one is a crank end pressure, right? This is cylinder vibration. You'll know where exactly your valve events are. So in first case, it's a suction valve head end opening. Then this one is a discharge valve crank end opening. Then here, suction valve head end closing and discharge valve crank end coding. And subsequently, you have the other event in one cycle. So when I say one cycle, it is a complete crank rotation of 360 degrees, right? And when you look into this picture and plot a new picture, if imagine this is your good data and now you have a bad valve, so you will see either the high vibration and also the positioning of these valve opening and closing event may change. So when you look into the good behavior and bad behavior and having this graph in view, in mind, or in screen, you'll able to diagnose the issues on the valve clearly. Okay, so this is one of the examples that I placed in here. Like this is a good condition. So you have the valves. Now you must be thinking that why the pressure sensor are a little bit deviated, because there is a drift in the pressure sensor, but not going to that point. But this is the red signal, cylinder vibration. This light green is the pressure on the crank end. This orange, pressure on the head end. This is a good condition. And now this is a bad condition. You have a high impact at approximately at 40 degree of crank angle, where you have a suction valve opening event on the head end side. You will see that this line which is a line below the suction pressure, it is going a little bit down. What it indicates? It means that the valve is opening a little bit late. So if it is opening 40 degrees before, now it is opening approximately at 43 degrees. So it is opening late. Why? So when you look into the 3D waterfall plot, it looks like this one and you have a high vibration, but after that it goes down. So it is an indication that valve is ticking. There is some kind of an moisture in the gas which get ingress in the valve and forms an emulsion and it sticks. And over the time with the gas, this emulsion washed away into the discharge line and the vibration went back to the normal. But with this curve, you're able to deduce a lot of factors like what is the situation of valve, whether it's sticking, whether it's a damage, whether spring is broken or your maybe valve is totally destroyed when you have no pumping at all. Okay. So next is your crosshead cylinder piston rod position measurement, which is a proximity probe. Sometime you put from the top, from the bottom, right? If there is any debris or contamination in the cylinder, you'll able to diagnose that one. Hydrogen service, you have in some cases you have a lot of debris, even you have a moisture, and then you need to detect that moisture may affect your behavior of your vibration as well as ultimately inducing a stress on the piston rod, and subsequently you have a crack or broken piston rod. So this can be only achieved by the piston position measurement. Okay, any condensate or accumulation in the chamber you can able to diagnose with this one. Condition of the piston rod, yes, and rider rings, which is an I think always people ask how I can uh, extract the rider ring measurement with the piston rod position sensor. Now if you look at the signal, there is a two component associated with the signal. One is a single piston rod position. Okay, this is your DC measurement of that proximity probe, okay, which is called average position. And the second one is your dynamics, like this one. This is a dynamic. This red dotted line is an average or a reference value. This is your DC, and if you look at this signal, it is moving up and down. This is an AC component. It is called dynamic. This is peak to peak. And red one is a DC, which we call it as rod position. And some people call it as rod drop as well. Okay, so rod position, one component, and peak to peak is the second component. The machine trip on peak to peak, not on the rod position. So DC value never trips the machine, only the AC value trips the machine. Okay, and this signal can also be divided into 8 parts, or you can also use as only a overall vibration measurement. Like in this case, you see this vibration signal at some portion, the rod is having too much of dynamics. And this situation occur like you have a dynamic at some part when you have some kind of an debris sitting in the compression chamber or liquid in the compression chamber. Then you see this kind of a situation. Okay, so usually what we do, we divide this complete signal in 8 parts, and sometime we saw that some customer ask us, okay, we don't need 8 segmentation, we need only one value to trip the machine. That can also be done, but I think doing an 8 segmentation give you a good indication what's going on if there is a deviation happening. Okay, again the poles, then the rider rings would be calculated using this proximity probe, and this can be done by this method. You need to have a geometry of your cylinder, starting from the crosshead, cylinder, then packing, then your position of the sensor as well. And this is a basic overview or basic formula to derive the rider ring, where using a proximity probe looking to your piston rod. Okay, I'm sorry, I'm going too quick because of the timing, but anyways, this is an example. There is a calculation and the rider ring is slowly increasing. Initially it hits the first warning and then second warning, and somebody says, okay, we have something going on in the machine. They shut down the machine and found that they have completely wear the liner off. So it's really important parameter to plot, but need to be done in a correct way, like the dimension of the cylinder should be correctly inputted in the system, and system should be capable enough to perform these measurements or derive these measurements. Okay. Okay. So last but not the least is the pressure transmitters that are integrated to the compression chamber. Like in this case, you have a PTs directly integrated to the compression chamber using a Keeney valve. And in sub-big machine, we also use a strain gauge measurement to derive the pressure signals. So it will help you detecting the walls, condition of the sealing elements, efficiency or performance, and the clearance pocket unloaders or valve unloaders if it is in place. So if you have a valve unloaders, pressure signals are really good parameter to diagnose any abnormality in the unloaders. Okay. You derive the PT diagrams. So you have a pressure and timing diagram. You have a compression and then re-expansion and then the suction stroke. Right? This is a PT. What you saw in the previous slide using a vibration and the pressure, these are the PT diagrams. And then you have a PV diagram plotted using these sensors. Okay, you have a compression, output, re-expansion, and suction. Everybody knows about this curve. But how we use this plot to diagnose any thermodynamic property of the system. Okay, this is how what parameters we can derive it from. So if you look at this curve, you have a polytropic exponent 1 and polytropic exponent 2 in the compression line. Same way you have a polytropic exponent on the re-expansion line 1 and 2. We plot the slope of these component. These are called, usually we don't have an adiabatic process in any compressor system. So we have some losses. So when you have a losses, when it is more than some level, you have a change in the slope of these polytropic exponents. And we need to plot these ones. And we put a threshold on these trend lines of polytropic exponent. And once you have this warning threshold set up on these polytropic exponent, the system will issue an alarm and you will check the symptoms and what's going on, what's the vibration behavior, and what is the efficiency, if there's a decrease in efficiency, or maybe the machine is pumping too much or too less. All of things you will able to extract whenever you have an alarm on these polytropic exponent. Same way, you have a breakthrough points. It means where your suction valve is opening, and here where your suction valve is opening, and this one is a discharge valve opening. So these are called breakthrough points. Again, it is these breakthrough points are specific for each cylinder, right? At what crank angle these breakthrough points should be. If it is going up, if the trend is going up, means earlier opening or later opening, it means something is going wrong with the machine. And also, if you look at the green area, this is your efficiency, and this brown area and pink area, these are the losses. You can derive all these things from this PV plot. Okay, not taking much of your time. I'll go with one of the examples. So this is a two-stage compressor. The blue one is a first stage, and the red one is a second stage. And above one is a good condition, and the bottom one is a bad condition. Now, if you look, the positioning of the suction valve opening or a breakthrough point is changing right, in both the sides. And also the polytropic exponents are changing, right? So in this case, your discharge valve, this green, is should be open somewhere around how much? At 0.45. Here it is opening quite early. While the suction valve should open at this position, it is opening late. So now you need to imagine and need to think what's going on, right? So, and also your slope is getting more steeper if you compare with a good situation. So if you can tell me which valve it would be, it is a first stage discharge valve have an issue. Because it's an issue, you will getting a gas coming back to the compression chamber, and you will be able to get a differential pressure to open the discharge valve quite early. In other case, in the same way, when the gas is coming in, you are not able to achieve the suction at the time, and the suction gas is going past to the discharge valve, and you are not able to achieve the differential pressure to open the suction valve at the time. So here you have a leakage in the discharge valve. So I'm sure that this is very quick and very fast presentation because of the time we had, but we can do another session, a big session for explaining this in all detail. Just reach us to the to Andrew or maybe to me. You may get my email address from Andrew, but we are providing all these services. And if you install our system at your machines, we are having a customer support supporting 24/7, giving all kind of services. Okay, so I'm going back to the questions if you have any, because I'm already eaten up 1 hour. Yeah, it's a fast one, but guys, I'm really sorry that I have a lot of slides but don't have time. I'm really sorry.
Yeah, 1 hour definitely doesn't cover it for sure. I mean, that was a great presentation, great insight. I learned a lot for sure, because reciprocating is definitely different than centrifugal. So we did have one question or two. One question here from Christian Rafael Garcia from Total in Rio de Janeiro. So he asked about ultrasound for detecting issues with the valve. Is that something that you can implement?
Yes, you can do this ultrasound testing. I think people do. They take the portable devices and doing the ultrasound, but we are not actually doing that. But definitely, I think this is one of the technology that you usually do for acoustic analysis and valve testing. Sure, but we are not doing that.
Okay, something not in your Prognost system.
No.
Okay, fair enough. Yeah, anyways, the polls. I mean, we could have, we didn't have time for that.
Yes.
We're gonna wrap it up, but definitely, feel free to ask questions on LinkedIn, in the group, or on the company page. Ramneek can be available for any kind of discussions and questions you might have. So there's a couple of handouts, and as usual, we'll post this up on YouTube in a few days for future reference.
Yeah, and you can also follow our YouTube channel, and maybe you get some more information. Yeah, again, stating the same thing. It's very quick presentation, and I am sorry, I think I am not did the justice to the presentation. There's a lot of things to say, but only I'm always sticking to the time. It says, okay, now 40 minutes and 6:55. So that's the reason I swiftly went through whole presentation. But in any case, you feel there is some question to discuss, or we are open, and you can either maybe reach to the Reds, or you can reach to Prognost or Burkhardt Compression, as Burkhardt is our parent company. Okay.
Excellent.
Okay, well, thanks very much, everybody. And hopefully we'll catch you live in person in March, but we plan to also, want to broadcast simultaneously as well, and then record. Okay, thanks very much, everybody.
Thank you.